Hi, welcome to day 41. Today's episode is brought to you by the Greek letter Omega, which we're going to be using a fair bit today. Congratulations, at some point today, your graduate sign is probably going to be plopped down in your front yard. And what we're going to be doing to help you get to that graduation point is a lab. I'm going to demo a lab for you, and it's all about voltage, current, and resistance in a circuit. Now, first of all, let's go over some of the terms and some of the stuff we're going to be using in the lab. First of all, what exactly do we mean by resistance? Well, it's abbreviated with the letter R. Resistance is, as you can see, how hard it is for electrons to flow through something. Something with a big resistance, well, electrons don't flow through it very well. That would be like a piece of styrofoam. Something with a really low resistance, like a piece of wire, well, electrons would flow through that really easily. And resistance is measured in ohms, which is abbreviated with the Greek letter omega. And of course, the bigger the resistance or the more ohms something has, the harder it is for electrons to flow through it. Now, when we do the lab, we're going to be using a voltmeter. And a voltmeter, as you can imagine, it measures the potential difference or the charge imbalance across something. We're going to be using an ammeter, which measures the current through something, and it's called an ammeter because it usually measures the currents in amps. And remember, of course, resistance is how hard it is for the electrons to flow. Current is how many electrons are flowing, how much current is actually flowing. And these are the two big things that we're going to be using in the lab. And something else that you'll see in use today, although technically it's not really part of the lab, is an ohm meter, which measures the resistance of something. So in the lab today, we are going to be using a voltmeter, which measures potential difference across something in volts. We're going to be using an ammeter, which measures the current, or basically how many electrons are flowing in amps. And if I bring it closer, you can see that, yeah, it really is calibrated in amperes. And these two things, these are the stars of our shows. These are a couple of resistances. You can see this one is a 2 ohmer, and you can see that this one is a 5 ohmer. So this one has a bigger resistance than this one. It's harder for the electrons to flow through this one than this one. And over here, just for curiosity's sake, I have an ohm meter, and let's put it across the 2 ohm resistance, and you'll see, yeah, it doesn't give quite exactly 2 ohms exactly, but pretty close, 1.8. Let's put it across the 5 ohm resistance, and there we go, pretty darn close to 5, 4.9, sometimes even 5. And you'll notice if I connect myself to it, well, wait, I gotta change the scale. You'll notice now that I'm changing the scale. Take a close look at that. So it is reading ohms in mega ohms. Okay, the number you're gonna see is the reading in mega ohms. That's what that M stands for. The scale on the ohm meter now is going from 0 to 20 mega ohms. And if I hook myself up to it, let's see what I register. Yeah, I register like 0.9, well, somewhere right around, I guess a little less than 1 mega ohm. That's a little less than 1 million ohms. So yeah, it's pretty hard for electrons to flow through me, as you might expect. And let's do one more thing. I'm going to take the ohm meter scale back down to where it usually is. And if I connect the ohm meter across a piece of wire, a conductor, as you can see, it gives a resistance of 0, which is what it should give. A wire is a conductor. It lets electrons flow through very easily. Okay. Now that wire probably does have a really tiny resistance, but not enough for our ohm meter to pick up. It's essentially got a resistance of 0. What we have right here is the circuit that we're going to be using in the lab. Pretty simple circuit. We're going to have a variable power source, a variable voltage source. That's what the arrow denotes, the fact that it's variable. And it's going to be connected in our circuit to a resistance over here. And if we're actually doing the lab, I would tell you, be careful when you're handling the resistance, because resistances, they get hot. Remember, that's what resistances do. They convert electrical potential energy to heat energy. Now, as far as measurements are concerned, we're going to use a voltmeter to measure the potential increase across the source. Remember, electric potential is increased across the source. We're going to use a voltmeter to measure that potential increase. And you'll notice the voltmeter, it is in parallel. And you can imagine why we say that it's in parallel, because geometrically speaking, it is paralleling the source. Regardless, the voltmeter is in parallel with the source. Whenever you're using a voltmeter to measure the potential difference across something, you have to put it in parallel with whatever it is you're trying to measure the potential difference across. So our voltmeter is going to measure the potential increase across the source, and then later on what we're going to do, it's real easy. We're just going to take the wires from the voltmeter and flip them from here over to here. Instead of having the voltmeter in parallel with the source, we're going to have the voltmeter in parallel with the resistance. And of course, when it's over here, it's going to be measuring the potential decrease across the resistance. Remember, electric potential is decreased across a resistance, and yeah, the voltmeter is going to be used to measure that. We have one other thing in the circuit. We have an ammeter in the circuit, and we would say that the ammeter is in series with the rest of the circuit. Basically, we had to break the circuit apart and stick the ammeter inside and close the circuit up again. And the ammeter is going to measure the current through the circuit. Whenever you're using an ammeter to measure the current through something, you have to, break that part of the circuit apart, stick the ammeter in series with it, and away you go. Now, of course, it doesn't really matter where we put the ammeter in the circuit, whether we have the ammeter here, or whether we have it here, or whether we have it here, or whether we have it here. The current is the same everywhere throughout the circuit. Remember, current is basically electron flow, and it's kind of like a water pipe. If you have so much water flowing through the pipe here, well, as long as you don't have a massive leak anywhere, or somebody running some other hose into the pipe, if you have a certain amount of water running through the pipe here, the same amount of water is going to be running through the pipe everywhere. So I have my ammeter here on the circuit, but it doesn't really matter where you put it. The current, the electron flow is the same everywhere throughout, because let's face it, where are the electrons going to go? They are stuck inside the circuit flowing around it. The electron flow is the same everywhere. The current is the same everywhere. I'm just about to build the actual circuit, and one thing I should point out is that when you're actually building a circuit is, however the diagram is drawn, you put the circuit together exactly the same way. For example, the voltmeter, the red or positive terminal of the voltmeter, it's going to go to the red or positive terminal of the variable voltage source. The black or negative terminal of the voltmeter is going to go to the black or negative terminal of the voltage source. As far as the ammeter is concerned, remember the main wire that's going to be leading out of my power source here, it's leading out of the positive or the red terminal of the voltage source. It should wind up on the positive or the red terminal of the ammeter, and of course then the rest of the circuit just follows from that. And resistors, they don't have a positive end or a negative end, so there's no big concern there. But the thing is, when you're putting together an actual circuit, is make sure you just follow along, and however the circuit is drawn out, make sure that you put it together the exact same way. Here's the circuit all set up like it's supposed to be, and if you compare the connections here compared to the connections that were on the diagram, they are exactly the same. Naturally, the wires and everything look a little bit different in real life, but the connections here, they are exactly the same as the connections that were on the diagram. And let's take a look at what we have here. First of all, you'll notice that it is the 2 ohm resistor in place, and you can see that the potential difference across the source right now, the potential increase across the source is 1 volt, and the current going through the circuit is a little bit less than half an amp, 0.4 amps. And you're probably not at all shocked that when I increase the voltage, the current increases too. Decrease the voltage, the current also goes down. Increase the voltage, current goes up. Decrease the voltage, current goes down. And you can imagine why that happens. Remember, as I'm increasing the voltage, basically what I'm doing is I'm piling more charge on to the positive terminal of the source, or pardon me, more positive charge onto the positive terminal of the source, more negative charge onto the negative terminal of the source. I'm getting a bigger charge imbalance, more positives and more negatives pushing and pulling the electrons around the circuit, thus more current. Okay, now let's take our voltage increase, let's take it back down to exactly 1 volt. Okay, so we've got a potential increase of 1 volt across the source, so we should have a potential decrease of 1 volt across the resistance. Let's see if that's actually going to happen. Okay, so hook the voltmeter up in parallel with the resistance. And yeah, pretty darn close to 1 volt. That's just what we expected. The potential increase is equal to the potential decrease. Okay, but you'll notice that it is a little bit less. And why it's a little bit less, well, that's something that we'll talk about for later. Okay, we're gonna come back in just a bit with the 5 ohm resistor in place. Okay, here's the same setup with the 5 ohm resistance in place. You'll notice there, 5 ohms of resistance. Okay. And you'll notice the potential increase across the source is 1 volt. So we got 1 volt's worth of charge imbalance pushing electrons. But you'll notice with the bigger resistance, we got way less current, right? That current, if you take a close look, probably hard for you to see, it is like 0.15 amps. Last time it was pretty close to 0.5 amps. So kind of makes sense. We've got over double the resistance that we had compared to last time. So yeah, we've got less than half the current we had last time. And of course, same thing applies if the voltage increases, the current increases, not quite as fast because there's more resistance. Okay. And again, let's compare the voltage increase across the source, the voltage decrease across the current. So how about this? Right now, I've got a voltage increase of 2 volts across the source. Okay. And let's see what the voltage decrease is across the the resistance. Should be very close to 2, probably a little bit less. What do we have? Oh yeah, there we go. Perfect. Very close to 2, a little bit less. And again, so that verifies the idea that voltage increase is equal to voltage decrease. And the reason, of course, they aren't quite equal is because there's a little bit of potential decrease in the wires. So you've got a potential increase of 2 volts across the source, a potential decrease of 1.8 volts across the resistance. That's because there's also a potential decrease of 0.2 volts across the wires. Now, for the most part, when we do calculations, we're going to ignore the potential decrease across the wires. But in doing the lab, you can see that it is there. Well, if you see me around town over the summer, you're gonna have to buy me lunch because I did the whole lab for you. With the 2 ohm resistance in place, I adjusted the voltage source so that the voltage decrease across the resistor was equal to 1, 2, 3, and then 4 volts. And for each one of these voltage drops across the resistor, I took a look at the current through it, and then I did the exact same thing for the 5 ohm resistor. These are the voltage drops through it, and these are the corresponding currents through it. Okay, as far as the graph is concerned, both sets of data are on this graph. This line represents the 2 ohm resistor. This line represents the 5 ohm resistor. And as you can see, the graph is the voltage drop as a function of the current. Let's take a look at the line from the 2 ohm resistor. Now the slope of this line is going to be the rise over the run, and if you do that calculation, you get 1.9 volts per amp. Notice the units. Okay, to calculate the slope, I went the rise, which is change in voltage measured in volts, and to get the run, that is a change in current measured in amps. So the units of my slope, 1.9 volts per amp. And then if you do the same thing for the 5 ohm resistor, you get a slope of 5.4 volts per amp. Now you'll notice that the resistor and the slope are very, very close to each other. There's only a 5% difference there. Over here, same thing. Okay, the resistance and the slope are very, very close to each other. There's less than a 10% difference here. If you were to do this lab extremely accurately with top-notch equipment and not make any errors, you would find that your resistance and your slope would be exactly the same thing, okay? Your resistance and your slope, they would be exactly the same thing. So mathematically, what can we get from all this? Okay, well, take a look over here. Okay, we know from the lab that if you have a graph, the voltage drop across the resistor as a function of the current through it, you're going to get a nice straight line. The slope of the straight line is going to be equal to the resistance. Well, in math class, what's the equation of a straight line? Well, it's y equals mx. But of course, we don't have a y-axis, we have a v-axis. We don't have an x-axis, we have an y-axis. So the voltage drop is going to be equal to this slope times the current. Remember, the current is equal to, remember the slope is equal to the resistance. So the voltage is equal to the resistance times the current. Or more commonly, it's written like this: V is equal to I times R. This is called Ohm's law. And remember, that V is the voltage drop across the resistance. That I is the current through the resistance. And R, of course, is the resistance itself. And that is the main thing that we want you to come away from this lab with. V is equal to I times R. Ohm's law. The voltage drop across a resistor is equal to the current through it times the resistor itself. A couple other things that you should know from doing the lab is that the units of the slope of our graph in this case, or the units of R, are volts per amp, and an ohm is actually 1 volt per amp. If something has a resistance of 1 ohm, that means it takes a potential difference of 1 volt to drive 1 amp of current through it. If something has a resistance of 3 ohms, well, that's equal to 3 volts per amp. If something has a resistance of 3 ohms, it's going to take a potential difference, a charge imbalance equivalent to 3 volts to drive 1 amp of current through it. So overall, since the beginning of the unit, that's 2 classes, we want you to remember 3 things. Number 1, around a circuit, the voltage increases are equal to the voltage decreases, or the potential increases are equal to the potential decreases. Same way of saying it. We want you to remember Ohm's law, V equals I times R. The voltage decrease through a resistor is equal to the current through it times the resistance itself. And we want you to realize that an ohm is equal to a volt per amp. There is absolutely no assignment to go with this. Just make sure you know what we've done here and you understand it. We will see you again tomorrow. Bye for now.